Section 2.11 The reversible adiabatic expansion and compression of an ideal gas. Adiabatic means Q is 0, dQ is 0. In that case, du equals dW. And then dW is equal to negative P external dV. And because we mentioned this process is reversible, for a reversible process, P external is equal to P. So we have du equals dW equals negative PdV. And also du is equal to CV dt. Again, for an ideal gas, you only depend on temperature. And du is always CV dt for ideal gas, no matter what kind of processes this ideal gas undergoes. Now we have two equations for du. du is CV dt because it's an ideal gas. du equals negative PdV because Q is 0 and this is a reversible process. Therefore, this negative PdV is equal to CV dt. So over here. Do we integrate both sides right now? Do not do that because this pressure is not only a function of volume but also a function of temperature. We cannot integrate these two sides right now. We have to rewrite this pressure to be nRT over V. And again, you see there are two variables, temperature, volume in the equation. Now, separation of variables is extremely important. So we move all the T's to one side, all the V's to the other side. And then we got this nice equation here. CV dt over T is equal to negative nRdV over V. Now we can integrate these two sides. Again, over here, there's only one variable T. On the right-hand side, there's only one variable of V. Therefore, we can integrate this to be CV ln Tf minus T initial. This one is negative nR times ln Vf minus ln V initial. Now we move this CV to the right-hand side. We get the logarithm of the ratio of temperature is equal to a constant times the logarithm of the ratio of volume. And then we get Tf over Ti is simply Vf over Vi to the power of negative nR over Cv. All right? So, if you know the ratio of V final versus V initial, if you know the value of Cv or Cvm and the initial temperature, you will be able to compute the final temperature of the ideal gas after the reversible expansion or compression. For convenience, we set this gamma, coefficient gamma, to be Cp over Cv. For ideal gases, gamma is equal to Cv plus nR over Cv. The reason is, for ideal gas, Cp equals Cv plus nR, Cpm equals Cv plus R. So when we do this, we see gamma is greater than 1. Gamma is 1 plus nR over Cv. Also, you can say gamma is equal to 1 plus R over Cvm. Cvm is the molar heat capacity under the constant volume condition. Now, for monatomic gases such as helium, neon, argon, gamma is 2.5 over 1.5 because Cvm of those monatomic gases is 1.5 R. Now we have the value of gamma for monatomic gases. For most diatomic gases, this Cvm is 2.5 R because of the rotations. So we have 1.5 R from translation and 1 R from the two rotational modes. Cpm is Cvm plus R. Therefore, we have 3.5 over 2.5. This is 1.4. Now, we have this gamma, and gamma is simply nR over Cv. So somehow we can replace this NR over CV with just gamma minus 1. And negative NR over CV is simply 1 minus gamma. Therefore, the temperature ratio is the volume ratio to the power of 1 minus gamma in a reversible adiabatic process of ideal gases. Look, this gamma is greater than 1, so this 1 minus gamma is negative. When the system expands, temperature decreases. This is understandable because if Q is 0, okay, and then the system expands and does work to the surroundings, the internal energy of the ideal gas should decrease. That means the temperature should decrease. Now we can look at the ratio of pressures. Because PIVI equals nRTI, PFVF equals nRTF, because again the system is an ideal gas, so regardless of the state, PV equals nRT holds, and then we can somehow rewrite TF over TI to be PV over NR for the initial state over PV over NR for the, this is PV over NR for the final state over PV over NR for the initial state. And then this TF over TI is the VF over VI to the power of 1 minus gamma. And then somehow by looking at this equation, NR and NR cancel. We have this equation. Now both sides divided by the ratio between VF and VI. Now we get the ratio of pressures is equal to VF over VI to the power of negative gamma. We can also easily prove that TF over TI, the ratio of temperatures, is equal to the ratio of pressures to the power of 1 minus the reciprocal of gamma. Okay, you can do this derivation easily. Now in summary, in a reversible adiabatic process of an ideal gas, Q is 0, du is equal to CVdT, and we can compute delta U given the initial and final temperature. Work is same as delta U. How about the delta H? Well, delta H is simply delta U plus delta PV. Delta PV is delta nRT. Delta nRT is just nR times delta T. So again, if you know initial and final temperature, you will be able to get delta U first and then delta H.